So the next thing that we need to look at is the enthalpy of displacement. I hope we can comfortably tackle a question to do with the enthalpy of combustion, definition and even the calculation. We can tackle a question to do with the enthalpy of neutralization. We can define neutralization. We can also tackle a question to do with the same. Now if that can be done, then we can comfortably move to the next thing. That is the enthalpy of displacement. The first question we need to ask ourselves, and that's a very simple question, is what is displacement? Now displacement, for the lack of a better term, I will talk of replacing it. So it's a replacement, it's a process whereby you replace. So in a displacement reaction, more reactive substance replace a less reactive one. And because this reaction is always going to involve solution, then we can say that it is going to replace a less reactive one in a solution of its compound, or in a solution that contains its ions. So we could talk of a substance A, and then we have a compound BC. So this one is in solution. So if A is more reactive than B, then A will replace, it will displace B. So then we are going to have B on its own, the elemental form. Then we are going to have a compound of A. So A has replaced B, A has displaced B. But the correct term to use is displace. So we call that a displacement reaction rather than a replacement reaction. We don't have a replacement reaction. So that's a displacement reaction on order of reactivity. Now, and this one is for a metal. Now, I've come across another displacement reaction that depends on volatility. Now, when you did the chemistry of hydrogen chloride, how did you prepare hydrogen chloride? By displacing it from its salt using sulfuric acid, because hydrogen chloride is more volatile than sulfuric acid. So the sulfuric acid displaces the hydrogen chloride. The same will happen with nitric acid, but that is another type of a displacement reaction that depends on volatility. So, but the ones that you're going to talk about in this particular session will be displacement reaction on order of reactivity. So, what is enthalpy? The standard enthalpy of displacement. So, there we are. That is going to be our working definition. So, the molar standard enthalpy of displacement, that is delta H naught D, is defined as the energy change. So we will talk of the energy change because we don't want to commit ourselves. But I think for all displacement reactions are going to be exothermic. So you can say energy produced. But to be on the safe side, because this one will apply to all reactions. So it's energy change when 1 mole of a substance is displaced from a solution of its own ions under standard states, from a solution that contains its own ions. So we are replacing it from a compound, and then the state must be the standard. So we can give a number of examples, and you can think of quite a number. So we can displace copper. Copper can be displaced by zinc. Why? Because zinc is more reactive than copper. So you see we end up with the element copper and a compound of zinc. Now, what do you do when we wrote the ionic equation? Just remove the spectators. So this one split to copper 2 plus and the sulfate. So we can remove the sulfate. The sulfate can cancel because it doesn't change. Not like I've seen many students do, writing 2 plus here. Starting with zinc instead 2 plus and then copper instead 2 plus. Surely, an element cannot consist of ions. Because how are ions formed? By the transfer of electrons. So when you are talking about the copper metal, what has it transferred the electron to? It must have lost the electron. But whom has it lost the electrons to? So you cannot have ions when it is in elemental form, when it's an element. When it's an element, it cannot be an ion. So those who write 2 plus and 2 plus and then they get a lot of, it's a bit confused. You don't know which one to remove. But the metals are not in form of ions. So another example of a displacement reaction is a displacement of copper with magnesium, and there'll be so the enthalpies will be different. Now the amount of energy that is going to be produced is dependent on the difference between the reactivities. So zinc is less reactive than magnesium. So the difference between zinc and copper is less than the difference between magnesium and copper. So you are going to get more energy in the second case when you displace copper using magnesium than when you displace copper using zinc, because of the difference in reactivities. The difference is and that is what I'm saying. The reaction between magnesium and copper 2 sulfate produces more heat than the reaction between zinc and copper sulfate. Why? Because the amount of heat produced will depend on how far apart are they in the reactivity series. The posokamazil haicom. Zil high comma. So if now let me put the copper there. The difference between calcium, copper and potassium is different from the difference between calcium and copper. So if I'm reacting calcium and copper, I'll get X kilojoules. If I'm reacting aluminium and copper, I'll say get Y kilojoules. But you see the difference here is smaller than the difference there. So you are going to get, this one is going to be greater than that, because it has to do with the difference. It has to do with the difference. So you cannot really talk of the enthalpy of displacement of copper. You must talk of the enthalpy of displacement of copper by a given substance, because it's going to vary depending on what you are displacing it with. Now, of course, in this topic, what you are interested in is the enthalpy of displacement from empirical data. So let's start with an example. Calculate the enthalpy of displacement of copper by ion if 0.4 grams of iron powder is added to 25 cubic centimeters of 0.20 molar copper 2 sulfate. The temperature increased by 8.5, and you're given some data there. Now, by now we know how to go about it. The first thing is to get the mass. So, okay, the first thing, our first objective will be to get the heat produced or absorbed. This time I think it's the heat absorbed by water or solution. So the heat change is given by mc delta T. Now, what is the value of m? Now, we said that get to the thermometer, what is the thermometer surrounded by? Yeah, by now we know what to do. So, what is the thermometer surrounded by? And now it is surrounded by 25 cubic centimeters of 0.2 molar copper sulfate and 0.4 grams of iron. So, I think somebody will be tempted to add them up. Now I want to add one other thing. Ignore solids. Let me underline that. I don't know how you speak in bold capital letters. Anything that is solid must be ignored. Ignore solid. Ignore solid. Always ignore solid. So you don't add up. Not like we were doing with the sodium hydroxide and hydrochloric acid. We are adding the two up together. When it is a solid, you ignore it. You ignore it. Furthermore, it's going to be in excess. You don't know its specific heat capacity and all that. So you always ignore any solid substance. So our M value therefore becomes 25. What do I want to work with? I want to work in grams. So 25 times the density, that comes 25 grams, times the specific heat capacity, which is 4.18. So work with what is given, not what you memorize. Grams per water. No, so these are joules per grams per Kelvin, times the change in temperature, which is actually 8.5 degrees Celsius, but which I said the change in temperature in Kelvin is the same as the change in temperature in degrees Celsius. So the K and K cancels, the G and G cancels, and now this gives me a value of 888.25. 888.25 joules. That amount of heat is what is produced during that reaction. What is the second step? The second step will be to get the amount of substance that is reacting. And I have two options. I can use the 25 cubic centimeters of 0.2 molar copper sulfate to get the number of moles of copper ions, or I can use the 0.4 grams of iron to get the number of moles of iron. Now the question is, which one do I use? Now so in this case, I have, like we did in the previous section, we will need to get the number of moles. We know the reacting ratio is simply 1 to 1. We have copper 2 plus 1 magnesium to form magnesium 2 plus copper. That's the ionic equation of the reaction. So the ratio is 1 to 1. Or is it magnesium or it's iron? Okay, it's iron that is reacting. The ratio is 1 to 1, so the number of moles must be equal. So, but let's work out the number of moles. So we want to work out the number of moles of copper. The number of moles of copper 2 plus will be 0.2 times 50 over 1000, which of course gives me 0.005. What about the number of moles of iron? Now the number of moles of iron 2 plus will be 0.4 over 56. And what is that equal to? I think that works out around 0.0007. And you can convince yourself that that is what you have. Okay, so which of these substances is in excess? Definitely, the ratio should have been 1 to 1. The ratio should have been 1 to 1. So we should have 0.05 of that and 0.005 of that. So it's like now, if we write what copper 2 plus with an no, there are 5 copper 2 plus, 5 copper 2 plus, 5 copper 2 plus. Okay, if I take it literally, 5 copper 2 plus, and how many iron? We have 2, 3, 4, 5, 6, and 7. So that reacts with that, that reacts with that, that reacts with that, that reacts with that, and then therefore those two will be in excess. They will remain unreacted. So I cannot react all the 0.07 moles of iron. I will only have to react 0.005 because the ratio is 1 to 1. But supposing the ratio was 1 to 2, like I had silver, say, let me change this to silver, and I still have 7 silver. I still have 7, suppose it was silver, I still have 7 of them. One react with 2, so those two will react with that, those two will react with that, those two will react with that. Yeah, so of course I'm talking of silvers. So I will need another silver, so all this will react, all the silver would have reacted, but the copper would have been in excess. But in this particular case, of course, we have discovered that the iron is in excess. The iron are in excess, so all the copper are going to react. So we therefore say 0.005. Are you really speaking? We are saying 8.25 joules. So what about 1 mole? 1 mole. Yeah, that is of course kilojoules per mole, not. So these now the energy per mole, and of course I've divided by 1000 to convert these to kilojoules. So small k, capital J. Is it exothermic or endothermic? Definitely, it has a negative enthalpy change. There is an increase in temperature. I can go on to draw the energy level diagram, but that is what we do in that particular question. So the most important thing in this is to remember that if it's a solid, you ignore. Then you apply the rules as we have done. The procedure that we have adopted in all the other questions we will apply, but only ignore any sorry. Now the next thing, let's do an experiment to determine the enthalpy of displacement, and I will still use copper, but this time I'll displace it using magnesium powder. Now, so I'll have 0.5, some 50 cubic centimeters of 0.5 molar copper sulfate, or copper 2 sulfate for that matter. I'll displace it with magnesium. I'll use 2 grams of magnesium, and it is going to be in excess. So I don't have to calculate. I've already been told that magnesium is in excess, but you can still work it out and confirm that the magnesium is actually in excess. So how am I going to run this experiment? Now all I will do is to measure the 50 grams of copper 2 sulfate, and I've done that. I will get the temperature of that solution. Then I will introduce the magnesium, all of it. At the same time, I'll start the watch. Then I'll be taking the temperature at some given time intervals. So because the table looks so big, I want to run that experiment for quite some time. So I may even need 2 pages. I will have a table that looks like that. That is a table I'm going to use. So I'll take the initial, and I expect you to get this data from the experiment, because I'll give you a script that you shall use to extract the temperatures at the various time intervals. So for the first 0, 0.51, 1.52, but then after that I'll go to minutes, because the change in temperature looks like it is not very pronounced. It is not really. So the first few are rapid and very high, very fast rises in temperature. For the others, the temperature changes are not as pronounced. So I've changed from 30 seconds to a minute. So we'll complete that data, after which we'll need to draw a graph. So let's look at the grip and complete the table. I hope you first pause and draw the table, then extract the data in the course of the experiment. In this experiment, the enthalpy of displacement of copper by magnesium will be determined. So I have 50 cubic centimeters of 0.5 molar copper sulfate, to which I'll add excess magnesium powder. So I'll expect us to be correcting the data. Make sure that you record that initial temperature and the temperature reading every 30 seconds. So I will add the magnesium and start the watch. Be keen to take the reading every 30 seconds and complete the table. The color definitely fades. Why do you think we used excess magnesium? And that is the type of data that I got. You can compare yours with mine. Now, how will these be marked? Of course, it will carry around 6 marks also. Around 6 marks. There will be 3 marks for completing that table, as long as you have actually done. Remember, we said in the previous that there is a way of knowing that you did not do the experiment. Like if this value is too much, is too high, or all the values are constant, or all the values are less than 10, all values above 70. There are always ways of knowing that you did not do the experiment, and there will be penalties so that you can lose the 3 marks anyway. Now the other mark is for the decimal, and this is where I'll be looking at, is it to either whole numbers on one decimal place, not two, not mixtures. So that is a decimal. Then there will be a third mark for the thread. What am I expecting in this reaction? I expect the reaction to continue, an exothermic reaction to continue. There will be a rise in temperature. But you will get to some time where the reaction will be over. There will be no more rise in temperature because the reaction is over. Then from there, that solution should start cooling to room temperature. Because if I left that solution forever, it wouldn't remain at those 40s, 50s degrees Celsius for a very long time. So and that's something you need to be careful about, because sometimes you do an experiment and it stagnates. Like mine was trying to stagnate at 47. It was stagnating. So what you must do is ensure that there is at least one drop. How do you ensure that? Now don't ask me. You must ensure that in the course of that experiment, there is at least one drop. Of course, if it was endothermic, you must ensure that in the course of the experiment, there is at least one rise. If it was an ectothermic, there is at least one rise. You must ensure that. Don't ask me how, but that must be done. But mine, I don't have to force it, because I can see it stagnated. Then there was a rise, stagnant, and then at least there is a drop in temperature. Of course, the last mark is the accuracy mark that will be marked at that point. The value that nobody loses. You can't lose that, because as long as you're doing the experiment, you can't lose it, because you are at liberty to just check that temperature like 20 times. You're not in a hurry. There is no stress. Nobody is rushing you, so you can take your time and take that initial temperature. As long as the apparatus are in good working condition, you will never lose that mark. So what is the next thing that I need to do is to plot a graph of temperature against time. Temperature against time. That is what I need to do. So I've been given a graph paper. Ensure that you plot the graph of temperature against time. Temperature against time. But in chemistry, we always tell you temperature on the vertical. We don't even tell you y-axis, because some people may not know. We will tell you temperature in the vertical axis against time. So if you lose that, it is your own choice. You have just chosen not to follow the instruction, because who doesn't know what vertical is? Well, you normally sleep vertically. When you sleep horizontally and you walk vertically, so you are vertical. So horizontal should not be confusing to any person. Now this is the type of graph I got. That is my type of graph. Remember how the graphs will be marked? Scale, axis, and plot. Now, do you think I have a good scale? Now, have I covered 3/4 of that paper? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 boxes out of 12, 13, 14, 15, 16. 11 out of 16, that is more than half. So at least I have half a mark. But before I confirm that, is it consistent to Is it consistent? 0, 1, 2, 3, 4, 5, 6, 7. Yeah? I have a scale there. 20, 25, 30, 35, 40, 45, 50. I have a scale also on that particular side. So I have a consistent scale and it is accommodative too. So I think I've earned the full mark. So note, if you start from 0 there, you do not write the 20 here. You don't write it. Then you write the 20 there. It's okay. But, okay, so if I have a big 0 there, then I write a 20 there. Then my scale is going to be wrong. What makes that scale wrong? Because from here to here I have 20. But from here to here I have 5. So the scale is wrong. Unless I break that scale, alright, as I've done, I write 20 there. This side is starting from 20, the other side is starting from 25. Now that is a scale. Axis, did I label the axis? Yeah, time in minutes, temperature in degrees Celsius. Right line. So draw the line and the arrow, then indicate, label your axis. Now, did I plot? Yes, I think I plotted up crosses, though you cannot see them. But when you get to my paper, you will see that they are X's. By the way, if the plots cannot be seen, they are not there. You just traced it. Like the way you are seeing it, like the way I'm seeing my plots here, they are simply not there. They are simply not there because they cannot be seen. Now I have ensured that the plots are more feasible points. So now the question of choosing what points to use. What points do you want to use to draw your lines? Remember, there's supposed to be 2 straight lines that you definitely extrapolate. Now, I chose this one. I could have chosen this one and this one. Because apparently I'm only going to use two plots for this particular line. I'm only going to use 2 plots. So this, if I use this and that, then they are going to meet at a plot. They're going to meet at a plot if I use these 2. Now the ones I've used, could also have chosen to use these 2, although I think in that case it's going to be lower than the highest plot. So I must ensure that it is not at a plot and it's above the highest plot, and that is it. Now let's use a graph now. I want to get the maximum temperature. I don't need time. I don't really need the time. I just need the maximum temperature. So I said here, I said before that you need to show. And what is that? That is around, that's not really around, it is exactly 47.5. So from the graph, I've read 47.5 as my maximum temperature. So you go to the answering of the question, determine from your graph the change in temperature, the highest change in temperature. So that is 47.5 minus 20. Yeah, there are people who forget to subtract the initial. You just read from the graph and that is all. So you get a value like 47.5. But you have been told to get the change in temperature. So you should have that in mind. And that gives me 27.5 Kelvin or degrees Celsius, all they are the same thing. How much heat is produced during that reaction? So remember, I used 50 grams of the copper 2 sulfate. Now, and I added 2 grams. I just said ignore any sorry. So that is times 4.2 or 4.17. I should have been given times, it should be always be given. So that, can even divide that by 1,000 at the onset. 5.775 kilojoules. Now, by how many moles of copper sulfate? So, because I want to get the molar enthalpy, so 0.5 times 50 over 1,000, that is equal to 0.025 moles. So 0.025 moles produce 5.775 kilojoules, about 1 mole. Negative 231 kilojoules per mole, and that is what it's going to be. So we can therefore go on to draw the energy level diagram and write the thermochemical equation as the next question requires. So having done that, we can wind up with that last question. Make time to do that. Determine the molar heat of displacement of copper given that when excess zinc powder is added 25 of 0.2 molar copper sulfate, the temperature rose from 22 to 25.